Thank you. Thank you for the introduction, Dima. So yeah, I want to start this 2-hour lecture in a sort of interactive way, as much as we did last time. So when you hear the word symmetry, what is the first impression that you have in your mind? Like snap impression. It can be an image, can be a sound, it can be anything that comes to your mind. What is anything? There's no right or wrong answer. What is the first impression? Go ahead. Okay. All right. So yes. So like a face, for instance, yeah. with the eyes. Yes. You want to say? Go ahead. Of the word symmetry. Like, can you describe it? Okay. Okay, that's a fair answer. Another one, maybe. Go ahead. A fractal, yes, that's a very complicated example of symmetry, like with self-similarity. And I also thought about fractals. I was about to miss them. These are some pictures that I came up with over the last week. So we have a very simple structure, a nice crystal, snowflake, with relatively simple symmetry, so rotational symmetry around an axis by a certain discrete angle. The full angle divided by 6, that's the angle that you can use to rotate the snowflake into itself. I also wanted to start with this example because it is not only aesthetically beautiful, but it is also showing in some disguise the structure of the frozen water molecules inside the ice that are responsible for the shape of the snowflake. Then we have the third example in the middle. Can you tell? This is of everyday use in our house. And this is the microscopic zooming in to the object. You find it in the kitchen, and it is a crystal. Salt, yes, table salt, yes, with atoms of sodium and chlorine, in a cubic cell, in a cubic pattern, and then repeated macroscopically. This is a bit more complicated, but I like it. It is a fullerene, an example of fullerene. It looks like a soccer ball, but it is made of carbon atoms. Then we have this fancy picture that I was about to miss. You know the molecule, you know the story behind it. You're about to say something? No. This is benzene. The chemical formula is relatively simple. It's a ring of carbon atoms with hydrogen around. But the story behind it, again, tells a lot about how symmetry is ingrained into our mind. Because the discoverer of this formula, Kekule, 2 centuries ago, was a German chemist. He thought for many years, as an anecdote, he recounts that he thought for many years about the problem of determining the formula of many chemical compounds, including benzene. And he came up with the idea of a snake chasing and seizing its own tail in a cyclic fashion. And that's how we came up with this idea of the ring of carbons for this element. Then in the second line, we have examples that need little introduction, the DNA with the helical symmetry, then examples of symmetries in animals, in nature, the bilateral symmetry that we were mentioning before, like for us, humans, dogs, cats, horses, most of the animals, including bees, and also the hexagonal symmetry of the honeycomb, which maximizes the use of space, but minimizes the need of wasps to construct the honeycomb. Stellar symmetry for animals with little to none locomotion, and then fractals, like exhibited approximately by branches popping out of trees. But not only in nature we find symmetry, we also find close to us in our society. This is an example of translational symmetry, but in time, not in space, the heartbeat. In psychology, this can be seen. What do you see in the second picture at the top? Psychological test. So you can see a vase or two faces staring at each other. Then games, board games. This is a flag. You know the flag. This flag is locals. It's the flag of the city of Stockholm. I also discovered it myself. I didn't know there was a flag for the city itself. And then other examples I took from visual arts, ceramics from Alhambra, Escher, a tessellation of the plane. This is famous for tessellations of the plane with very complicated patterns. Human constructions, again, visual arts, movies, cinema. And I actually discovered that there's a branch of cinematography that studies symmetry to construct scenes. So to distribute objects and people in a scene, also in covers, billboards, to communicate different messages. So there are these geometric patterns that convey different. How you place the objects along these diagonals, like it creates different emotions or conveys different messages to the spectators. Anyway, so these are all examples of symmetry that help us to understand what is, at least in geometry, what are the two fundamental players. So first we need an object, take the snowflake, an object that we want to call symmetric. The object itself is not enough. We need a transformation acting on the object that brings the object into, again, itself so that we can compare it. In the case of the snowflake, it is a rotation by a certain discrete angle. And in that case, yeah, for that transformation, we find that the snowflake goes back to itself, at least in the shape. I mean, the atoms, the molecules, they change place, but the shape remains equal to itself. So in this case, we say that the object, the snowflake, is symmetric, and we found a transformation, which is a discrete rotation, full angle divided by 6, that leaves the object invariant, that makes it symmetric. Okay. There is also another takeaway message, and this feature is more or less shared by all these pictures. These are, I think, if not all, virtually all, these are examples of discrete symmetries. There is a transformation that is not continuous, it is discrete. And indeed, to start appreciating what are the typical flavors of symmetry, I want to start with a little classification, not too big, but just to get a few things done on the table. So discrete symmetry, it's the one that we have seen in these pictures. It's easy to understand. I also hope that the people at home can see. If I take a card, the ace of spades, there's little I can do. Let's talk about rotations. I can essentially rotate the card by 360 degrees. That's the only thing I can do. There is only one symmetry here. If I take another card, the Queen of Hearts, I can rotate by 180. That's good. I can also apply another 180, and I get 360. Also 360, as much as for the ace of spades, was a good symmetry. In mathematics, we study discrete symmetries using discrete groups. Groups are mathematical structures, abstract mathematical structures, that are in essence a set of operations. Set of abstract operations, you don't need necessarily to refer to physical objects, and they obey some rules. So for instance, when I said that we have a 180 as rotation, as a consequence, I have also that if I combine two, I get 360, and 360 was another thing that I took into account. So they obey certain rules, and they can be studied using mathematics. The same goes for continuous symmetries. Take, for instance, a tire, forget about the rays in the middle. I can rotate it by an arbitrary angle around the axis, any angle, 1 degree, 2 degrees, the full rotation doesn't matter. It's an example of continuous symmetry. And the same in 3 dimensions. I can take a ball. Again, forget about the grooves. Just imagine that it's a perfect sphere. I can rotate it along 3 axes. If this was an aircraft, you would call it yaw, which is this, pitch, which is this, and roll, which is this. In geometry, you can call them Euler angles. But anyway, this is the essence. And for continuous symmetries, we have something slightly more complicated that are called Lie groups. In the case of the tire, we have a group called the U1, is the group of rotations around an axis. And for the sphere, for another three-dimensional object like sort of symmetric aircraft, whatever, you have the SO3 group. Another distinction between space-time symmetries and internal symmetries. Most of the symmetries that come to our mind, and I think all of those at the beginning, are examples of space-time symmetries. Usually space, like moving an object in space, like translations and rotations. But remember when I showed the example of the heartbeat, that is an example of translation in time. But again, you can associate it to a symmetry. We have also more complicated symmetries like parity, which is mirror transformation, so swapping left and right, when we made the example of the face with the eyes, or with the hands, looking yourself in the mirror. And then we have another set of symmetries that are less obvious, they're somewhat less close to our everyday experience, but nevertheless, they enter physics and they give effects. I will show you. They take different names. We have different symmetries, also depending on the model. Flavor symmetry, gauge symmetry, maybe supersymmetry realized in nature. These are symmetries that act not on shapes, objects, or space and time, but they act on the properties, what we would call internal degrees of freedom in physics that you can think of as properties of particles, fundamental particles. We're going to see some examples to make this clear. Okay, before we dive into physics, again, we stay a bit general. So why do we, maybe I should ask, why did you come here today? So why symmetry we think that is so important to study, worth studying? The first point is a bit general, probably a bit too generalistic, but I wanted to make it anyway, rather than omitting it. Saying this very general, we can say that it happens that the human mind is very keen on abstraction, symmetries, categorizing objects into boxes, kind of minimizing the energy, the mental energy to remember and to play with the word, to act on the word. Think of, for instance, the symmetries in mathematics, and going back to the ancient times. If I have 3 apples and 4 pears, I can associate 3 and 4 symbols. Addition is symmetric, and you can add 3 plus 4 or 4 plus 3. The result is the same. I have abstract numbers with symmetries encoded into them. If I can take multiplications, I can, for instance, measure the area of the rectangle. You may say, why do I care about the area of the rectangle? Well, but you can measure the area of agricultural lands. You can make people pay taxes, or you can organize the society at large. Or think of regularity in time, symmetries in time, like the raising of stars, like of Sirius in ancient Egypt, that was signaling the start of the flooding season. So symmetry has deep consequences, and we better tune with them, and also for our society, for our living. Anyway, the other 4 points are more physical and more concrete. And we're going to see all of them. So symmetry has the power, we see, not only to organize, this is already a big step, but also to weed out, to eliminate candidates of potential, candidates of natural laws, requiring a thing which is called the principle of covariance. This is a sort of a level 0 requirement for physical laws to obey. If they don't obey this criterion, for what we know, they're not supposed to be realized in nature. So we already weed them out. The second point is that symmetry helps us to predict the future, or at least to constrain it, because we will see that symmetries are related to conserved quantities. So if we have a dynamical system, or even the whole universe, or system in the lab, to stay concrete, and it is very complicated to solve and to predict it in the future is a very complicated procedure, challenge. we can nevertheless invoke conservation laws. So at least we know that some quantities will be conserved, and maybe they will allow us to find solutions much easier than solving the equations of motion, the dynamical equations of the system. Again, we'll see an example. The third point, physical point, is that symmetries helps us to write models. And I think this is the prime example is the case of the standard model. If we had to figure out all the possible interactions between all the possible particles, would have been a real challenge, almost impossible. But we can ask mathematics to produce for us models that have certain symmetries. And then starting from that, we can sort out which is the model that adheres to reality. This is already a big step, big preliminary step. The last point, I think it is less, if you knew about the first 3 points, the last point, I think it is a bit more specific to theoretical physics, but it's also an hallmark of theoretical physics, is the power of symmetry to classify or even predict the existence of particles. If we believe that there's a certain symmetry, then it follows naturally that they can be classified according to some criteria, and maybe also predict the existence of particles, or maybe build accelerators that help us to look exactly for that process and yes, find that some particles exist. We see examples. Okay, so this ends sort of introduction. Let's start with the first point, the principle of covariance. So the principle of covariance is a general principle, a method, a set of rules that allow you to tell how the perspective changes when we change observers. Different people like you, me, we are observing the same phenomenon, but we have different we are different observers in different frames, and we want to know how we describe this phenomenon and how to relate the descriptions. It is not said that we describe it in the same way. We also want a way to communicate with each other. Let's start with the main macro example about space-time symmetries. You can do the same also with internal symmetries, like gauge symmetry, but since gauge symmetries are less obvious to visualize, let's stay in space and time. And let's repeat what has been formulated by Galilei in his book, in his masterpiece in 1632. So this is what in retrospect we call the principle of Galilean covariance, Galileo's covariance. So in his book, one of the days in which the book is organized, he imagines the following example. So suppose that you are, as in the first picture on the left, suppose that you are sitting inside the main cabin of a large boat, a large ship, below the deck. And suppose that for now, this boat is close to the shore and we are at rest with respect to the shore. So suppose that I'm on the ship and you're on the shore. Okay. Inside the cabin, I can do experiments. I can, as he says, have some flying animals, flies and butterflies flying around in all directions. I can throw a ball at my friend on the boat. I can have some incense with the smoke coming up vertically. The same thing you can do on the shore, and you would observe the same thing. And now the genius of Galilei is to say, let's set the ship in motion. Let's make it proceed smoothly over the body of water without rolling or any other perturbation, perceptible perturbation. And now the thing is, this is where the principle of covariance enters. What he says is that myself on the boat, I want to observe any change in all this phenomena. I don't need to throw the ball with more energy if I point at the back or point at the front of the boat. Still the animals fly in all directions. The smoke raises vertically, not bent, and so on. So this is what we physicists say the equivalence of inertial frames. The ship and the shore are inertial frames, and we have phenomena that we can describe in the same way. It will be a bit more clear at the end of the slide. So after we state the equivalence of these two frames, let's come to our descriptions of the same phenomenon. And here the description change, because as long as I'm on the ship and the ship is at rest, I can hold this ball in my hand, and I let it drop. Okay, and it falls vertically down. You observe it falls down vertically. I observe it falls down vertically, following my body falls on my feet. But now, if I set the ship in motion and I'm on the ship, while I'm doing the experiment, try to do without throwing the ball somewhere. If I'm proceeding with some speed and I throw the ball, it's difficult to perceive it, but for you, the ball makes a curve, which is a parabola. You see, because the ball keeps going. But for myself, the ball still follows my body vertically. So we have different descriptions. For me, the ball falls vertically down to the ground. For you, follows a parabola curve. But the two descriptions should be equivalent. I mean, I'm a legit observer, you're a legit observer. So what's going on? What's going on is that if I make experiments on the boat, you make experiments on the shore, we would come to the same equations of motion, to the same dynamics, which is Newton's law, F equal to ma, where F and A are measured for me on the ship. You would do other experiments on the shore with balls and so on. You would come to a similar law, F prime equal to M prime. I put the primes to denote that these are quantities that you measure on the shore. But you see, these are two equations that we come up with by doing experiments, myself on the boat and yourself on the shore. And these are the same equation. The force is proportional to the acceleration acting on the body. So why the motion changes? Then I come back to this equation. Why the motion changes? Well, the equations are the same, but the initial conditions are different. For me, the ball was still in my hand. So when I let it go, it goes down vertically with no horizontal motion. But for you, the ball adds some horizontal velocity. So when I let it drop, it still has this motion, residual motion. But the equations, that is the force of the gravity force, and the fact that it has a vertical acceleration of 9.8 meters per second square, is the same for both. We have two solutions of the same equation. A few things about this equation. So this is an example of a vectorial equation, because the force and the acceleration on the body, in this case the ball, are vectors, loosely speaking arrows with a certain direction. It is a differential equation because, now speaking a bit of math, the acceleration is the second derivative of the position. So you have to solve for the position. It is not one of those simple algebraic equations that we like in high school. It requires some differential calculus. And as in many laws in physics, there's a say peculiar division, splitting between what causes the motion that sits on one side, the force, the gravitational force in this case, and what is the effect of the force on the body in the case of the ball, which is the acceleration and the parabolic of the straight line motion. Physical laws reflect, although they don't necessarily state, actually they don't actually state that, they reflect some causal relation between in phenomena, in nature. So, and equations reflect, if you want, also this kind of expectation. Okay, so that was what I wanted to say about Galilean's covariance. Then the same principle was generalized, including electromagnetic effects, to resolve some paradoxes. We can go through that, but it is not super important. So now we are allowing also experiments like electric wires, batteries, electromagnetic waves, radio waves, light bulbs, anything concerning electricity and light. So if you would write the Maxwell's equation, they would take the same form in both inertial frames. If you have been at our lecture on special relativity, you know that when you start speaking about high speeds, so you don't have a ship, but you have a spaceship. like in sci-fi movies or whatever. Now you have also to take into account other effects that they become significant at high speeds. That is time dilations and length contractions. So the perspective is not as simple as we stated before with the line and the parabola. It becomes a bit more complicated. You have a new absolute velocity, which is a postulate. The speed of light, or better, the speed of massless particles is the same in all inertial frames. Vectors are not enough anymore. You need an upgrade version of them, which is tensors. This is because they don't really like transforming well when you have space and time considered on equal footing. So you need objects that treat space and time on equal footing, which are tensors. And you can write, using some redefinition, you can write a sort of analog of Newton's law with some caveats on how you define the force and acceleration, and also how you define the mass. This is the rest mass. This is the mass of the ball that you measure on the scale when the ball is still in your hands. Historically, there have been a different definition of masses, also longitudinal and transversal mass that was depending on the speed of the object, but this is the simple definition of mass that we have in mind. Okay, what is left to include? Gravitational effects, so gravity and effects of gravitation. So now you're also allowing for planets and other celestial bodies to orbit each other under the force of gravity. This is called the principle of general covariance. It is a further generalization and extension, more precise than the previous ones. And now you're also allowing the equivalence between all the possible frames. So your spaceship can accelerate, you can be very close to a black hole, you can do pretty much what you want. It doesn't matter. There's a way to communicate with each other and to transform a description into another one. That is, in some sense, a reflection of the fact that we can use different frames, different coordinates mathematically, but still these are sort of intermediate artifacts that we introduce in our description. They don't have really a physical meaning. That's why we can then transform one description into another one using some laws. Alexander Krikun on Sunday will speak about general relativity, if I'm right. That's the next lecture, so we'll tell a bit more. I don't go into details. Again, you have tensors that transform well under new, slightly more general transformations. And again, you have laws that are tensorial laws. And again, you have a sort of this nice feature of splitting the cause and effects. In this case, this is a law that obeys the principle of general covariance. This is a law that we will see next time on Sunday. On one side, you have the cause of the deformation of the space and time, which is mass, energy, also something else we will see that is inside the T. And on the other side, it is the effect, which is how the space is bent by the presence of the mass and the energy. Again, more to come on Sunday. This is a bit of summary of how perspective changes when we change observers, and including more and more phenomena. Now, there are laws that make the symmetries of our universe that are essentially reflected in these principles more explicit. This is the so-called Noether's theorem. Probably you have heard of it because it can be stated in a very simple way, and so with beautiful examples. So it states that whenever you have a symmetry, which is continuous, remember the example of the ball that I was turning in my hand, for instance. Whenever you have a continuous symmetry, this implies that there is a quantity that is conserved. You measure it at a certain time, you measure it some time later, it doesn't matter, it stays the same. For the case of time translations, when your system or even the universe at large is translationally invariant in time, you have a quantity which is conserved. We call it energy traditionally. When you have translations in space, when space translations are a symmetry of the system, so there's no point or region which is more special than others, you have a quantity which is conserved. It is actually a vector. It is called the linear momentum or momentum for friends. This is what usually Newton stated as his third law: the action is equal to the reaction. And you see it when we play pool. So there's a quantity which is conserved. there's the white ball was proceeding horizontally. After the scattering, this quantity in the horizontal direction is split between the two particles. So they both proceed towards the right. And if you look at the vertical direction, you see the motion at the beginning was only horizontal. So there was no momentum vertically. And indeed, after still the two directions, the two momenta of the two particles in the vertical direction, they adapt to zero. One is going up, one is going down. So this also puts constraint on the angles made by these balls colliding. This is the power of symmetry in action. There's an analog of this, not in space, but in rotations. So when the system is invariant under rotations, you have a quantity, which is the angular analog of it, which is angular momentum. You see, this is a usually common example that is shown maybe in high school and textbooks. So this man on the revolving chair has a angular momentum conserved. So why is he slowing down or speeding up? Well, precisely because the angular momentum has to be conserved. When he has the arms wide open, so he increases his sort of rotational inertia. He changes the disposition of the masses. In some sense, he's more heavy, it's an angular way. He has to slow down in a way that the angular momentum is conserved. And vice versa, when he pushes the arms back to the chest, has less angular inertia, so he can speed up in order to keep this quantity constant. And I want to finish this partial list by saying that we don't have necessarily to restrict to space-time symmetries, but there are as well internal symmetries, properties of the fundamental particles that imply other conserved quantities. For instance, the electric charge, and also another charge that is more, even more fundamental. That is fundamental as well, and it affects other particles. It is called a color. This is how traditionally it is called, although it has nothing to do with light or reflection. We will see some of this later. But I want to finish the list, the shopping list, with the motivation behind it, which is why do we care about this, revealing symmetries and then finding conserved quantities. I go back to what I said at the beginning in the why slide. So symmetries help us to predict the future, or to answer some questions on the future, or to put constraints on the evolution of a system. Suppose that the mathematical reason is that, so for people who are familiar with the language, conservation laws stating that a vector is equal to itself before and after some events, like the case of the scattering of the billiard balls. So these kind of equations are algebraic, like A plus B equal to C plus D. But the equations of motion, as I said at the beginning, they are differential. They cannot be solved like X equal to something with some formula. They require calculus, analysis, integrals, and derivatives. So solving an algebraic equation is much simpler than a differential equation. We cannot predict all the details of the motion by maybe studying the conserved quantities, but yet we can answer some questions. For instance, if I tell you that we are sitting here on top of the highest tower with a car still at rest, then you give yourself a little kick and you start rolling downhill, very fast speed. No? The question that I make to you is, can I reach the rightmost point over here? Can I go all the way through all these circles and these bumps and reach this point over here? So while you're thinking, if you had to solve the Newton's equation, this would have been a two-dimensional problem. It's relatively easy, I think, but still maybe would require some minutes, half an hour, one hour, I don't know, to write properly all the definitions, all the axes, all the conventions, and solving the relatively simple equations. But if you use the conservation of energy, you can tell me, if I start from here at rest, when I reach then this point over here, anyone, there's someone nodding. Is that yes? Yes. Because I can say here I have only potential energy due to the fact that I have some height. gravitational potential energy. When I roll down, I lose height, so I lose potential energy. Where does it go? It must be conserved. That's the trick. It goes into motion, into what we call kinetic energy, from the Greek related to the motion. So I speed up, in simple terms. I speed up, I always at a lower height, so I always have speed. Even here, I still have speed, and then I get to the end. So by just staring at the silhouette of the roller coaster, I can say, and using the conservation of energy, I can say, yes, I can reach the end. So I can conclude this in less than 1 minute rather than solving the equations. Of course, reality is more complicated, but you see the power of symmetry in this simple case. Here, maybe you could have done both cases, also solving Newton's equation, but think of more complex systems, maybe using conserved quantities is the only way to find the answer to some questions. Okay. While we are going towards the slowly towards the end of the first part, I want a bit to change gear and start with a part that I think it's very beautiful and also entertaining, hopefully. So this is about the last point in my wise slide. So symmetry as a way to classify particles. In this slide, fundamental particles. So if you go back to the people in the 20s that were struggling with quantum mechanics and axiomatization of quantum mechanics, also experiments, one was mentioned by Dima, Stern, Gerlach, they came up with a conclusion. They figure out that fundamental particles have spin. So they have an intrinsic angular momentum, like the person sitting on the chair before in the video. So they spin. Classically, you would say that they spin around an axis, like the Earth spins around the axis. So like something like this, okay, like a spinning top. Up to some points. I mean, this spin has no classical analog because for some particles they would need to spin with a velocity on the equator which is faster than light. So it cannot be a classical spinning, like a spinning top. But yet they appear to have so in experiments. We can detect it, usually via magnetism. It is an intrinsic quantity. You cannot change it, they have it. And it is quantum. What do I mean? You can show using the rotational symmetry, the SO3 group, that this quantity for fundamental particles, it obeys a certain algebra. There is a h bar, the constant, the Planck constant in the game, and it turns out that you can only take discrete values, what we call quantum values. I anticipate a bit below. You can take values that are multiple of 1/2 in some units, which is h bar. Okay. Okay, so it is an intrinsic spin. It is quantum. Maybe you could look bored. Do we care about this property? Does it have any? Well, it does have. It has many applications. These are techniques called the NMR, nuclear magnetic resonance. If you speak to a chemist, he would use these techniques to detect the electronic neighborhood of some atoms. So he would tell you the chemical structure just by looking at some frequency, some Fourier transform of the magnetic signal. But in our everyday life, sometimes we need some medical imaging techniques so to visualize the interior of our body. And this technique, by the way, I didn't know. It is known apparently as MRI. So they drop N and they add imaging I, because apparently nuclear scares off people. But nevertheless, it saves people. For this technique, you would be immersed into some magnetic field, a strong magnetic field. The nuclei of hydrogens that are everywhere in bloody fluids, so water and fats mainly, they would align with this magnetic field. Then there is a perturbation. They start processing in some way. They give back some magnetic signal, and this is picked up by the same equipment. You would have a reconstruction then of your internal organs and your fluids and so on. and it is non-invasive in the sense that there's no radioactivity, there is no X-rays. It is just measuring and playing with the spins of the protons inside your body. Anyway, this is a parenthesis also to tell you that if you need, if you will ever have to have this technique applied on your body, remember that at least it is an application of theoretical physics, okay, after many years after the discovery. Anyway, coming back to physics, this is the first player in this slide. The second player is what we call bosons and fermions, and indistinguishability of fundamental particles. This is very, I think, I don't know, I find it very nice. This is the first time you learn it, and maybe you sometimes you think about it. So quiz. Okay, suppose that I start with these two balls, sort of ping pong ball and a tennis ball. Easy questions, there's no trick. Are they distinguishable? Do you tell them apart? There are people nodding. Yes, also thumbs up. Yes, because of size and because of mass. I can tell you this is much more mass, slightly more mass. It's number 2. Are they, again, just spit out, are they distinguishable? There's no trick. Do you tell them apart? There are 2 almost identical tennis balls. Do you tell them apart? There's someone saying no, but I can tell you that this is a bit more squashed, for instance, and also a bit stained. So if I can give you to you, you would say, see, it's a bit black over here to the people at home. So if you look at them, you would say, yes, I can distinguish them. What I want to say is that what I mean by the stain is that ideally you can put labels. I can put stickers 1 and 2. So yes, I can still distinguish. But now let's go quantum. If I have an electron and a proton, can I distinguish them? I need some physicists. Yes, because they're oppositely charged, they have different mass, because one is in the nucleus, one is outside. And here comes the, the trick. If I have 2 electrons, can I distinguish them? Because for the tennis balls, we concluded it is stained, we can distinguish. But for electrons, can you label electrons? No, there are some people saying no, that's the correct answer, you cannot. Because they have the same mass, all electrons have the same charge. That's why we talk about the charge of the electron, not a charge of the electron as if they had many. They have only one. They are point-like, so good luck finding some internal structure, some excited states. So the punchline is that fundamental particles, electrons, quarks, and so on, are indistinguishable. And this has deep consequences. Again, as more than the MMR, actually. Why? Because fundamental particles then, so given that they are indistinguishable, they still have different behaviors, and they still classify into 2 groups. So we have bosons. I use some checkers, white checkers. Bosons. Bosons are particles, fundamental particles, for instance, that if I put them in a box, okay, if I put them in a box, I describe also 3 if you want. I can put them in a box. Let's start with 2 as in the slide. If I put 2 in a box, I have a mathematical description for them in the box. It is a wave function, but it's a wave function for 2 bodies. So how does it behave when I swap them, when I ideally change the label? So bosons have the properties that if I swap them, I replace their identity. Ideally, I replace 1, I put 1, I remove 1, and I put 1. The wave function is a plus sign. It's back to itself. Fermions, instead, they are a bit more tricky. And we see, thanks to them, we should be thankful to fermions. Fermions, instead, have a different property. When I swap them, ideally, they have a wave function that changes sign. Say, why do I care about these signs? You should care, because if I put 2 bosons in a box, suppose that I put them in the same state, the state to be, I don't know, pawns, to be on the ground state, the lowest rank possible, the lowest edge. this is a state which is allowed. Because why? Because if I swap them, I still have the same state. But fermions, luckily for us, they cannot. Because if I put them again, like bosons on the same energy level, in the same state, both poles, for instance, the ground state level, this is not allowed anymore. Because if I swap them, I still get the same wave function. So this is a state which is not allowed. I could have put, instead of a pawn, a bishop, for instance, and then build some linear combination to make it anti-symmetric. This would have been possible. Why do we care about this last box? Because this could have been an atom. This could have been 2 electrons, and electrons are fermions. And this, for instance, could have been the 2 electrons in the helium, around helium. This would have been hydrogen, this would have been helium. When you add more and more, they start filling all the electronic shells, starting from the innermost to the outermost. Why do we care again? We care because the outermost shell gives rise to chemistry. It tears apart with its nitrogen and oxygen. Chemistry doesn't care about nuclei, it cares about the electronic shell that stays outside. So chemistry, as we know it, exists eventually because matter is made of fermions, and fermions are indistinguishable with this definition. It is also responsible, and we mentioned, I think, last time, for the stability and volume of matter. If I hold my mobile phone in my hand, it doesn't fall through my thumb and we become a sort of continuum blob. We don't get like fused into each other. It has a certain crystalline structure, the same for the desk, the table. I can stand here on my feet and I don't fall to the ground like 2 ghosts passing through each other. So this minus sign seems innocuous, but it has bigger consequences for life as we know it. The other nice thing that we can again appreciate with a little demo is that there's a theorem now to relate fermions and bosons and spin. There's a theorem that tells you that spin, that I remind you was quantized, can take integer values can only take integer values for bosons and half integer values for fermions, so 0.5, 1.5, 2.5, and so on. This is the so-called spin statistics theorem. And there's also, I forgot to say, another interesting property of the spin related to particles. So the spin tells you how a particle, that the wave function of the particle changes when you rotate the particle. So if you have a spin 1 particle, like a photon, you can, to get back the same wave function, you have to make a full turn. So spin 1 particle is like the ace of spades. A spin 2 particle, like what we hope is the graviton, since it is spin 2, I can only just make half a full turn. So 180, and it goes back to itself. What is funny is when, so you understand, the spin is related to the fraction of the angle. But now if the spin is less than 1, the angle should be bigger than the full turn. And that is what happens with spinors. So with spin 1/2 particles, like electrons, there's a trick that is called the plate trick. You can look it up. There are different ways to visualize this rotation. So spin 1/2 particles, you have to rotate them by 2 full angles to get back to themselves. Because if you just perform a full rotation, they get a minus sign in the wave function. And the way to visualize it, let's see if I can do it, is to hold a cup. You have to play with a belt or string or your arm, something that should be twisted, all right? So if you take your cup in this way, and then you rotate it clockwise once, you see that my arm is twisted. I didn't go back to the same configuration. But if I keep twisting, another full turn, and I go back to myself. So this is how you visualize rotations for spin 1/2 particles. Very strange. Anyway, going now towards the end of the first half, I mentioned important result by Wigner. So you can use space-time symmetries to classify all the possible particles by mass and spin. This is important because essentially we already know the properties of the graviton, the quantum of carrying the gravitational force, just by knowing that it is a spin to particle. So we already know many properties of particles even before their discovery. And I maybe mention this, then we can take the break. Using the connection between a spin and the division between bosons and fermions, we can also predict, so using symmetry, again, always symmetry arguments, we can predict something which would be very difficult to observe otherwise, or to predict. So this is a composite particle. It is a baryon. It is called delta plus plus, because plus plus is the charge, the 2 units of plus charge, which is made, if you study the quantum numbers of this particle, you would deduce that you have 3 quarks, u, aligned with spin up inside this particle, which is the delta plus plus. Would you object on this configuration for what you said before? Is it something allowed for the fermions? There's something fishy? Someone, yeah. So yeah, there's something fishy because they cannot stay in this state. It wouldn't be allowed. So what's the resolution of the puzzle? It is not by any means obvious. People came up with the idea that no, they are not actually in the same state. They are slightly different. They are in different states. So like bishop and knight, for instance, something like this. What is this different? With different. What is this extra property which should be different for all of them? It is a new quantum number, a new internal degree of freedom, as I was saying before, that people call the color, with the disclaimer that has nothing to do with colors. It's just a name. It comes in handy because this new property, this new quantum number, can take 3 values that we can conventionally call red, green, and blue. And it is a quantum number carried by quarks as well as gluons. This is a gluon, for instance, inside a neutron, as well as, for instance, inside the delta plus plus. It's exchanging colors, you see. So while it is traveling, it carries some color. So at some point, you have particles of the same quarks of the same color, but just because there is some residual color carried by the quark. And this is the mechanism of the strong nuclear force, stronger force. The gluons, which are the analog of photons, they carry the strong nuclear force. They bind quarks on a scale which is the scale of a neutron, essentially. Also, mesons, other particles have this characteristic length. And the strong force is so strong, that's why the name, it is so strong that when you try to pull apart quarks, new quarks pop out of the vacuum in order to create particles that are always white, that are always colorless. Because if they are colored, the strong would be so strong that new particles would pop out of the vacuum to make a colorless states. So that's a nice consequence of the use of symmetries for a quantity that inherently, because particles are colorless, cannot be observed directly. Okay, maybe with that we can take a pause now. Okay, so we finished the first part, speak about this new intrinsic property, which is named color. I wanted to tell you that it was very useful in hindsight, because this actually, I'm taking the idea from Dima that I really liked. Over the years, talking about the 50s and the 60s, there were hundreds and hundreds of new particles, in retrospect, composite particles discovered, like the delta plus plus, but many other cousins of a huge family. If you can see, this is actually a double column. So you have the particle and the antiparticle. So get ready for this huge number of dozens and dozens of particles many particles. You have a list in Wikipedia, and so a list that Dima was explaining, was going through last time. And these are 2 comments. One, I think, was shown by Dima, the one by Polly, the other one I also found in Wikipedia. So apparently going to botany was a backup plan for theoretical physicists back then. Anyway, I just found it funny to mention. But no, I mean, there's a lot of particles and a lot of confusion and headache for the people back then. But thanks to the fact that we think, I mean, we came up with a model that that has quarks as fundamental particles, we can explain all this zoology in a simple way. In some sense, people came up in the 60s with a sort of a periodic table, if you let me say so, sort of new Mendeleev table for all these mesons and baryons. And again, the classifying principle, without going into details, is lo and behold, is symmetry. So the 3 lightest quarks, the quark U, D, and S, are relatively similar to each other. And you can use this symmetry between the 3 which is called flavor symmetry, by the way, to classify the lighter mesons made of 2 quarks, that is, and baryons made of 3 quarks. So you have these geometric patterns, which are in some sense periodic tables, if you wish. They're organized in a way that I don't describe. But the official name of it is eightfold way. It was coined by Gell-Mann and other people, collaborators. This is also in a reference. I didn't know that. I only discovered a few days ago to the Noble Eightfold Way of Buddhism. So apparently there's also similar, I mean, it was taken from there as a sort of, not pun, but anyway, like a reference to Buddhism, because of the eightfold way to organize these particles in multiplets. And not only that, it was thought for a long time that other bound states could have existed. We just didn't know. We put them in some mathematical appendices in textbooks. And then later we moved essentially, if you let me say so, these appendices to the main body of the textbook, because what I want to say, these particles were predicted, and then we actually found them in nature. Remember, I was doing my PhD when the pentacore came out, so it was a memory. Anyway, to finish off this, morally speaking, this part, let me say then the real fundamental periodic table, so to speak. So the list of the particles, the real fundamental particles as we know it now. So we have quarks here in green. I shouldn't say green because it's also the color, but here up above, the 6 quarks. By the way, also the history behind quarks is kind of amusing. Gell-Mann, I think it was Gell-Mann, he had the pronunciation, he had the sound for the new particles that he thought about, but he didn't have the spelling. And in reading James Joyce, he came across this word quark, which has also a meaning in English. I didn't know. It's like the sound of the birds, of frogs. And he came up with this word. So if you can read the anecdote in Wikipedia, for instance. Anyway, we have quarks. These are fermions. We have also other fermions, which are leptons, here in red. The most famous is the electron. Leptons are called the leptons because leptos in Greek means like thin, small, because the electron, that was the electron and the muon, this is what they knew at the time when they coined this term, they are much lighter than those particles made by up and down quarks that are neutrons and protons. These 3 are charged, these 3 are chargeless, these are the neutrinos. So these 12, 6, 6, 12 particles are fermions. This is what matter is made of. Actually, I say 12, but remember, quarks, they come in 3 different species. So we don't have actually 6 quarks. This is usually sometimes omitted, but it's useful to keep in mind, especially in calculations. We have not 6 quarks, but 18 quarks. They just happen to sit at the same place. Then we have the gluon. Again, we don't have only one gluon because I remind you it is colored. We have actually 8 gluons if you do the calculation properly. This mediates the strong nuclear force. We have the photon. We know what it mediates. It mediates the electromagnetic force. We have the Z and the W bosons, W plus and W minus. This mediates the so-called weak force. We're going to find an example later with the example of the cobalt. And then the Higgs boson. We had a full lecture last time by Dima speaking about that. So this is what we think exists at fundamental level. These are point-like particles without internal structure, as far as we know it. And I forgot to say, these mediators of the force are bosons. Okay. With a twist, we have also antiparticles. So the game doesn't stop here. We have like a mirror table with the corresponding antiparticles. For the particles that where the antiparticle is actually distinct from the particle itself. It's not the case for photons. They're the antiparticles of themselves. But the story between the discovery and the prediction of antimatter and antiparticles is again dictated by symmetry. So it's useful to flash it quickly. So Dirac, again, we are going back to the good old days of quantum mechanics. Dirac is a big name, was axiomatizing his book, is essentially almost a modern textbook telling what is quantum field theory, how to do the fundamental operations on quantum states. Anyway, he was starting with a relatively humble problem, that is the problem of studying the light emitted by excited gases. We had many examples in the lectures, these spectral lines, different colors emitted by gases. He was trying to study the splitting of some lines in very close together colors. And he came up in his studies with a big result. He wrote the first consistent equation, quantum mechanical and consistent with special relativity, equation for the wave function of the electron. It is written on the commemorative plaque in Westminster Abbey in London. You can see it. It is close to the plaque of Thomson that discovered the electron, Maxwell, Hawking is buried there, and also other big names, British scientists. Anyway, in this equation, not really in this because all these constants have been put equal to 1, but there is H bar and C, the two constants, one of quantum mechanics, one of special relativity. Anyway, when he was studying this equation, he figured out that there are pairs of solution with energy plus E and minus E. So in particular, there are states with negative energy. What are those? And the genius said, these are actually physical states. We interpret them as anti-electrons. So he came up with a thought, with an idea that I think nobody before him came up with, the idea that there are antiparticles. For each part, he said for the electron, there is an anti-electron, a new species. So for the electrons, we know what they do. We had this demonstration with Dima. You can go and watch the video. This is a cathodic tube. And anti-electrons, they were discovered later. They have the same mass, you see, they have the same mass, but opposite charge. And they are bent in opposite directions under the magnetic field, but with the same radius of curvature, because the mass and the charge are the same up to a sign. And again, physical application, PET imaging. So if you undergo this imaging technique, you are injected, in contrast to an MR, now you are injected with some radioactive material, biological substances carrying fluorine, which is radioactive. It is synthesized in loco, because it decays very quickly. So you are injected. After a few hours, this material goes in some areas affected maybe by some problems in your body. And then this material beta decays. It emits anti-electrons. These anti-electrons, what do they do inside your body? They find the closest electron and they annihilate they create two gamma rays, two essentially photons, two photons. And these photons are detected by the machinery around you. So PET stands for positron, which is another name for the anti-electron, emission tomography, because it is emitted and it's a tomography, namely you are, morally speaking, you are like sliced into two-dimensional planes and then they're reconstructed three-dimensionally. To finish this story, sometimes it is not mentioned, but it is, I think, worth mentioning. Later, when Feynman started developing a quantum field theory, so systematizing quantum mechanics, if you want, in a much more deep way, Feynman, and again, I send you to watch the lectures that we had, he replaced the quantum waves with quantum fields and extended this idea of electrons, anti-electrons, essentially to all particles. The quantum field is a nice mathematical object that takes into account particles and antiparticles in the same calculation. We don't distinguish them in theoretical calculations. And a beautiful example that I have to thank Sasha Krekun for reminding me. We can have this diagram over here to the left. You have to follow the evolution bottom up. So you have two red lines, two electrons, so an electron and anti-electron, like that when you have a PET. They collide, they come to a region where they're very close together, something in the middle happens, I can describe. And what comes out are two photons. This is the process of annihilation. They get annihilated, they disappear into photons. This is PET, what happens in your body. And this is the same process, the same Feynman diagram, it is called. It is a mathematical expression. It is some algebraic integral expression, and which is simply rotated. Space and time have been rotated, and it describes a totally different phenomenon, but with the same quantum fields. Now it is a scattering. You have an electron colliding against a photon. They do something in between, I don't describe, and then they scatter off as a sort of billiard balls, in some quantum billiard balls. So you have the same mathematical expression, the quantum field that describes both positrons and the electrons. And I didn't know, but I found in my search for today, in quantum mechanics, in the old quantum mechanics, people took into account particles and antiparticles in different sums with different contributions. Nowadays, instead in physics, theoretical physics, we don't do so. We just have one entity, which is the quantum field, that permeates one quantum field per type of particle. So the quantum field for electrons, for quarks, and so on. Okay, so this with this, I wanted to finish what say a good chunk of the first part. The actual second part will be much shorter, but I think very entertaining. Oops, I spoiled. Can you answer the question on the slide? It is just a funny way to introduce the second part, but let me first explain the slide to get everybody on the same page. So the question is whether you can tell reality and whatever you want to call it, a mirror of the reality will be for us an example, or a dream, whatever you mean by that, an alternative reality apart. So here I took an example from two movies, two famous movies, to explain some concepts that are maybe a bit off our reality, but I will make them a bit more concrete and hopefully appealing. So two sci-fi movies, oversimplifying the synopsis. In The Matrix, you have people, in both movies, you have people in some sense living in a dream. In The Matrix, if I can oversimplify, you have humans living a dream, and they have no way of oversimplifying. They have no way by themselves to figure out that they are living in this alternative reality, like sort of video game inside a computer. Instead, in Inception, we have people like the role played by DiCaprio in this snapshot that has the ability to go into the dream and go back to the reality. How does it tell apart? Now, this is an old dilemma of philosophy. How does it tell apart reality from the dream? When we are dreaming, we actually think that is reality. No? So how can he snatch back to reality? Well, because he has an object, which is called the totem, I think, in the movie, for him, it's a spinning top. So he has a spinning top, and whenever he picks the spinning top, because maybe he's a bit doubtful about his surroundings, he spins the top. And if the top, like here, hopefully, stops moving after a while, it means that is in reality, there is friction. This is what we expect. If instead the spinning top keeps spinning, something that we would say it is unrealistic, indeed, it means that it's in the dream. So the difference that in one case, you don't have any object to answer this question. In the other case, in the other movie, you have, if you want, if you let me simplify the two plots. Okay, why does it have to do with physics? Okay, so I didn't tell you that in nature we have three fundamental discrete symmetries. One is charge conjugation, which swaps particles with antiparticles. So like in a snap, ideally, it swaps electrons with anti-electrons and so on. Quarks with anti-quarks, photons with themselves, because they're antiparticles themselves, and so on. The other is a parity. It is mirror symmetry, is swapping left and right. We made the example at the beginning with the bilateral symmetries, like looking at yourself in the mirror. And the last one is time reversal, which is like, I don't know, recording a scene, recording like a video, and then playing it in the reverse time direction, so the rewinds. Okay, so the question is, I could have made a quiz now that I think, but do you behave that these are symmetries of nature? So do you think that you can replace all particles with antiparticles, nothing changes? Can you swap left and right and you don't see nothing special happening? Can you reverse time? Well, maybe this is already a bit obvious to answer. So are they symmetries of nature? Fundamental level, at least. Fundamental level. Maybe you have in mind entropy, but here I want to speak about fundamental level, microscopic processes. So the way I want to answer the question, before that, I make the question to you. So let's forget about the two movies. Let's watch these videos. So I downloaded two videos, waves on the beach, and a woman writing on a scratch pad. So one of these two is the original video, the other one is mirrored, is flipped. The same goes for the person writing. So can you tell, let's start with the first example. Do you know which of the two has been mirrored, left and right? Which one is the original movie? Do you have any clue? One is the original, the other one has been mirrored. I can ask the same for the second one. Maybe the second one is a bit more, you have to be very attentive, very careful with the movements and so on. What would you say? Just shoot. I mean, we're just playing. Go ahead. That's very good. That's very good. Yes. Thank you very much. The 2 points. Great. We met. Yes, exactly. So this is mirrored. That's very good. That's very good. This is mirrored. This is mirrored. Yes. You maybe you can't see, but she's writing in Latin characters. So yes, she's writing in the opposite direction. There was also the subtlety. But no, the first picture you don't see, the first pair you don't see anything actually, or at least I don't see anything wrong. Indeed, I have to remind myself which one is the original. So yeah, so these two have been mirrored, but the other one are two the original videos. So in this case, you had like the spinning top of that movie, no? That was very revealing. These two features. I want now to translate this question into actually a problem that was formulated, I think, I won't say something wrong, I think in the 70s, when there were many people and many scientists searching for extraterrestrial intelligence, I mean, extraterrestrial life intelligent. So it's the SETI project. There was a problem called the Ozma problem. It was named after the name of the project. It was the project Ozma, using radioscopes to communicate with maybe potentially with extraterrestrial civilizations. And by the way, Ozma, it was also in Cascade, was named after the land of Ozma, a character in the land of Ozma, which is the land of Oz, which is the book after which then the Wizard of Oz was taken. So if you, yes, it's really the same name, but regardless of that, the problem is the following, and with that we are gonna carry it to the end essentially. Can you define, this was a series of questions for the researchers back there. So can you tell, so you have Alice, I forgot to say, you have Alice on Earth and Bob on some exoplanet. He's an alien, he's not a human, he's an alien living there. Can Alice define what is left and right operationally with some procedure and tell Bob, the alien on his planet? The rules of the game is that she can't send pictures, otherwise she could have said, she could have done what we did with the Pioneer 10 and 11. We sent golden plaques in the universe with a man raising a hand. You could have written below which hand was that. And also we cannot refer to shared pieces of the sky. Otherwise you could have said the same with the constellations. They are symmetric. So you could have said the brightest star is the one on the left or on the right. It is not by any means obvious, so I will go through the slides. So the first naive solution is that, just to set the ground, she says, well, she starts describing left is you are left-handed, the left hand sits on the left part of your body, some self-referential definition. Of course, this wouldn't work. Maybe Bob is not even a humanoid, is some blob, some monster, whatever. But regardless, even if he has hands or arms, he doesn't know what is left is right. You're just self-referencing what we know. You cannot even say the thumb is outward. I mean, these are definitions that refer to themselves. So level 0, yeah, it's very difficult. We cannot use a common language or common definitions that we agreed upon as humans. Second question, so she thinks, well, I can refer to chemistry, because in chemistry, we have chirality in molecules, in chemical compounds that are relevant for life. For instance, sugars, they are left-handed inside our body, inside the DNA. And the proteins have amino acids that are right-handed. So they're not, you have different versions, one the specular of each other. So she can say, well, it's easy. Look inside your body, take a little sample of your body and look at the molecule, and she can describe the formula. And then since the molecule is chiral, is asymmetric, you can give an explanation what is left and what is right. The heaviest atom is on the left and on the right. But there's a problem. There's a problem. Because Bob may well be made of the same, of the molecules with the same chirality or not. I mean, we creatures on Earth are, I think all the species, all the life forms are made with a certain chirality. I think this is one of the proofs of the common, common ancestor, no, of life on Earth. But Bob may be made of the opposite chirality. And actually, if you think that this is strange, there is a short novel by Arthur Clarke called The Technical Error. He imagines that a scientist is doing some, is subject to some accidents in some superconductor facility, whatever, power plant. It's a sci-fi story. And in a snap, he gets mirrored, so he gets all the molecules in his body changing chirality all of a sudden. It has its own advantages because it cannot be attacked by viruses and bacteria. They cannot eat this poor technician, this poor scientist. But on the other side, he cannot eat. So he's starving to death very fast. He can eat, but he cannot assimilate because the lock and key mechanisms at biological level do not work anymore with opposite chirality. And you have to read the novel to figure out what he can do, if he survives or not, what is the end of the story. And at the same time, you also found funny that there's actually the sequel of Alice in Wonderland, since I'm using Alice, which is Through the Looking Glass. I don't know if she discusses left and right, but I thought that the title was relevant for today. Anyway, joking aside, chemistry, no, that doesn't work that well. We have to get smarter. And since Alice is a theoretical physicist, no, I'm joking. She says, let's use the weak force. Let's go down and down. Maybe we'll find what in our metaphor is the spinning top of inception. So, and she can remember that the weak force actually, here is the scientific point, breaks parity, the parity symmetry. In essence, back to the 50s, there was an experiment made by Madame Wu concerning the decay of cobalt atoms. This is a cobalt atom with a certain spin aligned along certain magnetic field. This decays by beta decay, weak interaction, mediated by one of these W plus and W minus bosons. This decays into nickel. And not only nickel, but we have also an electron and an anti-neutrino, anti-electronic neutrino. With the spins, for the symmetry again, it should be split in 4, 1/2 and 1/2 with all these directions aligned. But with the speeds, you see, the speeds are opposite for the conservation of the momentum. So you must have a neutrino going in one direction and the electron going in the opposite direction. The cobalt was at rest, so it didn't have any momentum, like the billiard balls at the beginning. So, of course, the electrons and anti-electrons are emitted in all directions, but let's focus on those processes where the decays happen along the line of the spin, the magnetic field. So this process, and this is actually, I think, a thing that we don't understand yet entirely, but when you have particles, the decay products emitted along the actual line, this is a process that always happens. You always have the anti-neutrino with the spin given by the left and the right hand rule, with the spin aligned with the red line, which is the velocity. The process in the mirror instead, so the process where essentially the two are swapped, doesn't happen. It's not that they have 50-50 probability, they're like 100% and 0 probability. So not only the symmetry is broken, you could have had 55-25 or 199. No, it is broken, it is maximally broken. It is maximally violated parity with 100% and 0 probability. Again, why it actually happens, I think we don't really have an explanation still after many years of studying and the standard model. But if you accept this fact of nature, that by the way is revolutionary because nature distinguishes left and right, this was also a shock back then. Well, you have a process that distinguishes left and right. This anti-neutrino, with the rules of the spin, essentially defines a corkscrew which is right-handed. So you can say to the alien, have a look at the anti-neutrino, or better, the electron, which can be detected. That would be the solution of the level 1. That would be the solution of essentially virtually in our universe. This would be the solution of the problem. If we have to be picky, there's an additional. If we want to be super fussy, there's an additional problem. Nobody has ever told us that Bob is made of matter. It could have been made of antimatter. I mean, as far as we know, antimatter is very rare in the universe, but who knows? Maybe I don't know. Anyway, for the sake of the argument, we can also assume that it's made of antimatter. And here's the problem. If it's made of matter, Alice could have said, do the experiment with the cobalt decay. Look at the electron, anti-electron, the parity of the two is opposite. Okay, so the left-handedness or right-handedness is opposite for the two. Just look at the charged particle and detectable, so it's not with neutrino. And okay, that's your definition of left and right. The problem is if Bob and everything on his planet is made of antimatter, there is no way to define what is matter antimatter for him. You're just telling some instructions to him via some radio waves. You're telling him what to do, and he finds the material in loco. So in the worst case scenario, he could have picked some some raw material from his mines and his planet. He could have synthesized radioactive cobalt that is actually anti-cobalt. And for anti-cobalt, you see the direction. I go back. You see what was for the anti-neutrino, the two arrows. For the neutrino, here the arrows are swapped. So in case, to summarize, is made of antimatter, Bob would come up with the opposite definition of left and right that we have. So technically speaking, we are not done yet. If we have to be super fast. And again, since we are theoretical physicists, she understands. They say, let's use again the weak force. Maybe we can find a process that I don't know, violates other symmetries. We can be more precise. That is independent on the fact that we are built of matter antimatter. And the solution is again the weak force. This is a funny way to explain another process that I think is very mind-blowing. It is related to the count decay. So she can say, and lo and behold, this is the solution. She can say, look at kaons. Kaons are particles. You can have the kaon or the anti-kaon, the neutral kaon and the anti-neutral kaon. And it happens that K0 decays less often in left-handed electrons. And lo and behold, it happens the same for the anti-kaon. It always decays less often into left-handed electrons. So that's the solution. She can say, take kaons. It doesn't matter if Bob comes up with chaos, anti-chaos, because the result is independent of his initial choice. He will find, Alice can say to the alien, look at the decay products. These are not only the possible channels, the probability goes up to 100%, but look at these particular channels of decay. Look at you will have particles, say for instance, she can say, you will have particles of opposite charge. Take the particle that the kaon decays less often into, and not only she can say what is left, she can also say this is matter, because in both cases the least probable decay channel is matter, is an electron. She can say it's an electron. She can say this is negatively charged, and we agree upon the definition of charge. And finally, we can also agree on the definition of what is left, what is right, because they are both left in both cases. So I went a bit fast because we are going towards the end, but I'm happy to, you will also have the video if you missed some steps. So the least probable particle is essentially the analog of the spinning top, if you want, that tells you clearly what is left, the definition of left, and in just a position what is right. I want to, since we are 29 now, again, a part which I hope it's entertaining. We are tired. Okay, so we sorted out CMP. So to summarize, P is violated. Also CP is violated. What happens with the time reversal? This was a video that was presented already a few times in our lecture, so I don't go through that. If we have a gas in a box, microscopic process, can you tell if this video has been flipped in time, if it has been rewinded, or this is the natural video that you can find in produced by Mathematica, actually? Can you see something strange with the time evolution in this? No, there are some people saying no. No, indeed. But macroscopically, we know if the arrow of time is flipped, right? if I throw this ball, it's already a bit squashy, very hard down here to the desk, I break it into pieces, I shatter it. You will never see the pieces going back and recreating the ball and jumping magically into my hands, okay? This is what we call entropy. No? The entropy is always increasing. And indeed, microscopically, we can clearly see if there's something wrong with the arrow of time. And I don't say anything about the movie, I don't want to spoil, but this is a movie clip from a movie where there's something wrong with the arrow of time. This is called the temporal pincher movement. You have to watch the movie and watch some explanations to properly understand what's happening. But let's just look at the video. So there are some soldiers fighting. They're in a sort of combat zone. There's already something weird happening, right? They're fighting, there's some rockets. They shoot a rocket against the building and the building goes up. Not only, then it also goes down. So you have, besides the movie, you clearly see that there's something very unnatural. So yes, microscopically, I want to say we can distinguish, we can tell apart if someone is rewinding a part of the surroundings. But my question, scientific question, is whether we can find something microscopically that violates time reversal. Because by the way, in this gas, we had some people nodding, they were saying, no, here, there's nothing wrong with reversing time. Like, you cannot really tell if I flipped the video after creating it with the mathematical script. But lo and behold, nature has some surprise. These leaves, we have B mesons oscillations. We have neutral particles, mesons, that can oscillate in the sense that they can turn into another particle and then back to themselves. So it's an oscillation in time, if you want. And they violate time reversal symmetry. You can create this state. It takes a relatively long time to get to this red state, but then a short time to get back to blue. If you rewind, you would see the opposite. It takes a short time from blue to red, and then long time from red to blue. So this is, and again, I think we don't have certainly a clear explanation for that, but there are also microscopic processes that violate time reversal symmetry. So many symmetries that we think are kind of obvious, left, right, but matter, antimatter, maybe it's less obvious, but time reversal microscopically, they're all violated by nature. And going to the I think last slide, let me say what is the moral of the story. So what we know now, what we think it should be correct, and it passed tons of validations and verifications, is that the combination of C, P, and T altogether is a symmetry of nature. So if you imagine to immediately, suddenly, to turn matter into antimatter, flip the arrow of time and flip left and right, then you shouldn't be able to tell that something has happened. So the combination of the three is a symmetry, but individually they're not. This is a symmetry encoded, and I conclude with the standard model, included in the paradigm, the scientific paradigm that we think describes nature at the most fundamental level. Inside the standard model, we have encoded Lorentz symmetry, so special relativity, and the language of quantum field theory. These two imply that you should have CPT combined invariance. There is another symmetry that I won't describe too much, but Dima has made many diagrams with that to explain it with complex numbers. If you watch the videos, there is an internal symmetry that has a complicated structure, or group structure. This is a symmetry of the quantum fields. Roughly speaking, you have a group for each of the fundamental interactions: strong, weak, and electromagnetic force. How this symmetry is broken, partially broken in some sense, better broken by the vacuum. We had a lecture about the Higgs boson. And I wanted to show you, because it's also at the end of the journey, also nice to appreciate. This is the mathematical expression, technically the Lagrangian, of the standard models. There are people also printing on t-shirts. It has a very long expression, you see, it is very, very, and I doubt this is like fully spelled out. I think this is still in a compact form, relatively compact form. And you know, each of these terms, they tell you how a bunch of particles interact. You can have like 3 particles interacting or more complicated interactions. Each term tells you what can happen, how they can couple with each other, what is the strength of the interaction by looking at the coefficient of this term, essentially. And yeah, so to end, this big writing was the product of imposing, sitting down with the sketchpad and imposing many symmetries. Lorentz symmetry, the language of quantum field theory, this big gauge symmetry, the mechanism of spontaneous breaking of symmetry, and imposing symmetry upon symmetry, you can write this long expression. Of course, there are still parameters left to fix, like the mass of the electron appears as a parameter, like x. You don't know what it is. You have to plug it yourself. But the parameters are very little compared to, to the infinitely many possibilities you could have come up with if you didn't impose symmetry in the first place. And again, symmetry predicting particles before the actual discovery, some quarks, the heaviest neutrino that was, the standard model was dating back to the 70s. The neutrino tau was discovered, I think, in 2000. The gluon jets, I think, shortly after the 70s. W and Z, I think, in 82 or in the 80s by Rubia. And the Higgs boson, it was the news of about 10 years ago. So with that, I thank the people who allow me to do research, this fellowship of the European Commission, with the disclaimer that they are not involved in the preparation of these lectures. This is just some legal disclaimer. Don't worry about that. And I conclude with the last slide, thanking Alexander Krikun, who's not here, but he helped me with the material and refining some ideas. I thank everybody in the team, starting from Dima. This is a collective effort. And I remind you that we are doing this series of lectures to support Ukraine and the victims of war. So if you want to contribute, please go to the website. You can contribute in a material way or more, financially, or more material in the sense locally, in a way that you can choose. We have some suggestions, but feel free to do whatever you feel like in line with your belief system, value systems. And also here, I remind you the disclaimer that this is part of a private initiative as private citizens. We are not this part of the motivation behind the lectures is not related, was not related to our employers, so Stockholm University and Uppsala universities and so on. And with that, I don't know if Dima wants to say something more, but with that, I think we can finish here and have some questions. We have some questions. Question. Sure. Okay. Any more questions? Yes. You say that if the whole CPT can be violated, this is the question I didn't like universe, everything yes, left and right. Yes. So that is about microscopic interactions. So if you look at microscopic processes, the claim is that yes, if you do these three operations at once, you wouldn't be able to tell. Like the process you end up with is a process that is legit and happen. The same probability of the process in the original universe, the original process. So it's another process because you change something, because you change matter, but that's another legit process to the same probability. The question would be whether, I mean, if you have something here going on, they do the transformation, you have something else. The question is still this process allowed or not, like in the original universe? And if the answer is yes, and we think it is yes, for the combined, okay, so we say CPT is an actual symmetry of the quantum theory and the standard model. This is the claim. Maybe you had something in mind. That's what I understand. But yeah, this is the actual claim. Yeah.
The universe can exist. The question: can you interact with it? So can Bob live in this universe? It's more tricky one. Can exist Bob who has CPT or full CPT opposite? Because he also has time opposite directions on it. So how do you speak with the Bob?
Let me be clear. Yeah, to this question, I don't know, but the actual thing is that you do these three transformations at once in the whole universe. So you cannot speak with a mirror version of Bob. You always speak with Bob in your universe, with the Bob that you encounter. There are no like different space-time regions where this is what the theorem says about having like patches of the universe where CPT is locally lit. I don't know. Who knows? You're suggesting some question to her.
That's a nice picture.
Okay. I thought you didn't want to make the question. You're telling your mate to make. I actually came into the cinema randomly because I wanted to go to that cinema, and I had to watch that movie. And yeah, it's very complicated. You have then to read the blogs and other people explaining with a lot of details, but still it's very confusing. I must say, very confusing. But I think it was kind of accurate according to the logic of it. Okay. So let's see some.
Yeah, the Ozma problem.
Yeah. So let me see if I. So in that example, he could have taken chaos on anti-chaos. The thing was that the result is independent of your initial choice, because you see, if you follow the yellow here, you always, regardless of what you start with, then the least probable channel of decay, which is 20.1, is always selected. So regardless of whether it was made of matter and antimatter on this planet, we would ended up, no, the initial state was different, but the product would have been the same. So that is.
Probably the question was, how can you be sure that he will not confuse it with Robinson's?
That's a good question. So you can, instead of say K0, that he doesn't know what it is, maybe call it differently, or maybe doesn't even have a voice, a pronunciation. you can say a particle with a certain mass made of two, let's say, valence quarks, or made of two quarks. I think it is. I think it is two quarks, whatever, made of certain composition of quarks that is created using, I don't know, certain, because kaons do not exist naturally, they are created in intermediate products. So I guess you can say, you give a recipe, like you build a certain acceleration with the electrons and protons and all these things, and you would describe operationally how to get to kaons. And if there are other products, you can say kaons are neutral, kaons have a certain mass, kaons are made of a certain number of quarks. So there's, if you want, a long way to describe a particle without actually pronouncing its name. If you, I guess it's like this. It's also new for me. I didn't know the full story behind it. I know bits here and there, but not the full problem, the solution. So I guess you can do that. Maybe I shouldn't say. I was also thinking that to polarize this, to have this initial alignment of spins, you should use magnetic field. I was also thinking in the back of my mind, if defining what is the direction of the magnetic field is parity invariant. Also, maybe as positrons in wires instead of electrons in wires. So you should think carefully if everything is well defined. Also things that I didn't think too much about. But I guess it works. It's a standard problem.
Okay. So can I make an announcement?
Please.
Yeah. So thank you, Eduardo, for the lecture. So this is part of the lectures, and we have 2 weeks left with lectures, and until now, so we are traveling using this 8-legged horse all through the nature, and until now we spent a lot of time and being very small. So we did quantum mechanics, we did quantum field theory, we did bosons and fermions, moving around. So yeah, so this is possible, this is not possible, right? Well, and we operating with both. Also, we did statistical physics, which means a lot of stuff, right? And we also were traveling very fast. So all this was done. Now we go to different directions. Instead of balls, we do something big. This Sunday, we will have lecture in Stockholm about gravity, and Sasha will explain how gravity is related to change in geometry of space-time. This will be in Stockholm. Next Friday, we will have true astronomers, not theoretical physicists, but the people who actually do measurements in the sky, who will tell us about evolution of universe and of stars. I spoke with them. It's really interesting what they can measure. So this will be next Friday here. In 2 weeks, on Sunday, we are going to speak about final lecture. Stockholm will be about theory of everything. We will try to combine everything together and tell what physicists know and want to know about the nature together. So we will combine all the small stuff with all this big stuff together. It succeeds, but it doesn't. And finally, on 10th of June in Uppsala, there will be a professional biophysicist who is going to speak about biophysics and how physics is used to study life. So you're welcome to come. You can join on Zoom or come in person. And thank you for coming today. Thank you, Eduardo, one more time.